The cosmos has a chilling way of revealing its secrets, and interstellar Comet 3I Atlas is currently articulating a profound enigma in a sudden, dramatic shift of hue. This shift, from a relatively common reddish tinge to an unsettling, vibrant green, is not merely cosmetic. It is a violent chemical signature erupting across the void, hinting at internal processes that stand in stark defiance of established cometary models. As this rogue wanderer plunges deeper into the solar embrace, heating is triggering a threshold event, a non-linear activation within its core that is shaking the foundations of astronomical theory. Its trajectory, marked by hyperbolic velocity, clearly flags it as an interstellar visitor, an object destined for a final departure, yet its current behavior suggests a profound, unexpected intimacy with the Sun's energy. Its journey, from discovery on July 1, 2025, as only the third confirmed interstellar object, has now progressed beyond simple observation into a state of acute scientific anxiety. This green light is a harbinger, a signal that the raw, unprocessed materials of another star system are being unleashed, forcing a radical re-evaluation of what these primordial voyagers are capable of concealing within their frozen hearts. Earlier photometric data from NASA's Atlas network had chronicled a gradual, expected evolution. The color index moved steadily from reddish values toward neutral, interpreted as the slow dissipation of dust from a newly exposed surface, giving way to icy grains. This was a progression that fit known models of dust liftoff and changing optical depth within the coma. But the new imaging and spectroscopic data have begun to indicate a startling, abrupt transition, a jump rather than a drift. The contrast is stark. One moment the coma is tinged red, the next it glows with a brilliant, disturbing green. This shift forces astronomers to confront more than a mere pigment puzzle. It raises critical questions about the physical and chemical machinery operating deep inside 3I Atlas. In solar system comets, dramatic green hues are often attributed to diatomic carbon, C2, which fluoresces intensely under solar ultraviolet radiation. However, in 3I Atlas, spectroscopic analysis has not yet confirmed the strong presence of these usual suspects. Instead, the emerging spectral fluxes are signaling the release of cyanide, CN radicals, and more unsettlingly, nickel atoms. The presence of nickel vapor is profoundly unusual. While many comets exhibit metals weakly, they are rarely strong enough to dominate the color signature. What is more alarming is the non-linear pattern of these species' appearance. Some analyses suggest their emission rises superlinearly, faster than simple temperature scaling, as the comet nears the Sun. This superlinear behavior hints at a threshold or switch-like activation process deep inside the body, severely unsettling those who expect a comet's interior to respond monotonically to increasing solar heating. The color transition, which coincided with the appearance of a visible antisolar tail and a significant break in the slope of the brightness curve, suggests a wholesale transformation in mass loss. Before this event, brightness rose steeply, consistent with dust liftoff from a reddened surface. Afterward, the growth rate slowed, consistent with a shift in the dominant scattering source, a new population of small, more transparent icy grains rather than the older, larger red dust. One prominent model struggles to suggest that early dust grains carried a red tinge, while the later, more vigorous sublimation of inner ices released bluer, more transparent grains, pushing the integrated color toward green. However, for many astronomers, this adjustment of dust and ice populations feels fundamentally insufficient to account for the abruptness of the color jump. The growing fear is that deeper, unexpected chemistry or internal structural features are revealing themselves, posing a direct threat to existing cometary theories. If 3I Atlas harbors volatile reservoirs or trapped compounds radically unlike those of Oort cloud comets, we may be witnessing a wholly new class of behavior. The green glow may be the definitive signal that exotic ices or compounds, dormant for eons, are now being violently unleashed, perhaps in scattered pockets or bursts, completely upending the assumptions about how interstellar bodies thermally evolve under stellar influence. Even more unsettling is the hypothesis that the object's internal structure permits a sudden, cascading propagation of heat or gas pressure. If the outer shell of 3I Atlas is unusually insulating, Heat could accumulate in subsurface layers until a point of critical pressure is reached, causing it to propagate through cracks or vents. This rapid opening of fresh, volatile-rich regions could cause spatially heterogeneous and temporarily abrupt color changes. Observers increasingly fear they have moved beyond a phase of gradual approximation and are now witnessing discontinuities, sudden jumps in activity rather than smooth transitions. The correlated presence of nickel, combined with cyanide emissions, may point toward exotic organometallic chemistry or the sublimation of mineral phases uncommonly volatile in typical solar system comets. These indicators suggest a surprising internal composition, hinting that the comet is not a simple, inert icy body but might harbor internal energy gradients or hidden reservoirs of volatiles that challenge our understanding. Of interstellar body construction and preservation, the anxiety culminates in the striking difference between 3I Atlas and its predecessor, 2I Borisov. Borisov's behavior was largely consistent with a cometary template, but the events unfolding with 3I Atlas feel far more radical, a color change happening mid-course, along the approach, rather than merely appearing green near perihelion. This dynamic behavior is not adequately captured by existing thermodynamic or dust dynamic models. The compelling, unsettling idea gaining traction is that 3I Atlas carried a primordial insulating crust that only recently cracked or peeled away as it warmed. This sudden exposure is unveiling a hidden interior rich in volatile, uncatalogued compounds, initiating cascading changes in gas release, particle production, and optical behavior. If this is correct, we are witnessing the real-time unveiling of a hidden interior from another star system, a process suggesting interstellar comets harbor structural and chemical diversity far beyond our solar system's analogues. The rapid rate of change suggests that the morphology and behavior are not solely controlled by external solar heating, but by internal dynamics. This dynamic, radical metamorphosis raises profound uncertainty in interpreting all comet surveys. If a comet's color can shift so markedly mid-course, historical observations might have systematically missed similar volatile phases in other, fainter objects. The most chilling anxiety is that this sudden color shift is merely a prelude to even more dramatic revelations, a definitive harbinger that 3I Atlas carries structural and compositional surprises not yet imagined. If its internal features contradict current paradigms, it will force a complete revision in how we conceive of interstellar body formation, thermal evolution, and internal chemistry. It demands a question. What new and potentially volatile mechanism is that luminous green revealing about the deepest, coldest reaches of the galaxy? And what does it mean that this object, now heading for its closest approach to Earth in December, harbors a material composition more akin to planetary matter than a typical solar snowball? Smash the like button and subscribe for all the latest updates on 3I Atlas. Your continued support ensures we can decode the next, possibly more profound, revelation this rogue visitor is prepared to offer as it completes its final, enigmatic pass through our system. Don't miss a single step of this interstellar confrontation with the unknown.